In this video, we are continuing from where we left off the other day. In the previous video, we have discussed the basic concepts of oxidation and reduction, as well as oxidizing agents and reducing agents. So here we are starting with oxidation number, or you call it oxidation state. This is the charge an atom or a group of atoms appears to have due to the number of electrons it appears to have gained or lost according to some arbitrary rules. Yes, we have some criteria for determining the oxidation state of an atom or a group of atoms. Number one is that the oxidation number of elements in their uncombined state is always 0. So we have it that sodium atom, calcium atom has oxidation state of 0. Oxygen molecule, hydrogen molecule, each of them has oxidation state of 0. The second rule is that in compounds containing hydrogen, the oxidation number of hydrogen is always +1, except when it is in combination with metals, then it is -1. For instance, calcium hydride, hydrogen there has oxidation state of -1. And the third rule we are discussing here is oxygen has a charge of +2 in compounds, except when it is in peroxide, that is where it will have -1. And the fourth rule says that the sum of the oxidation number of all the elements in a compound is 0. When you sum the oxidation numbers of every element in a compound, it gives you 0. And the fifth rule says that group 1 and group 2 metals always have oxidation states of +1 and +2. So sodium and potassium ions have oxidation states of +1, calcium and magnesium +2. And then aluminum in group 3 is always +3. The sixth rule states that the oxidation number of simple ions such as aluminum ion, copper 2 ion, calcium ion, sulfide ion is the same as the charge on the ions such as +3, +2, +2, -2 respectively. The seventh rule states that the sum of the oxidation numbers of the components of a polyatomic ion such as sulfate ion and phosphate ion is the same as the charge on the ion concerned. So let us consider some examples on determination of oxidation number of central elements. Let's consider here, we want to find the oxidation number of manganese in KMnO4, that is potassium permanganate. So we have it that potassium has to be +1 because it's in group 1 and oxygen is -2. You equate everything to 0 because it's a compound. Remember the rules? And you collect like terms and you see that manganese is +7. Please, it has to be +7, not just 7. You have to include the sign there. Now, the second example here is you want to determine the oxidation number of chromium in dichromate ion. That is here. You see the statement of the problem, and you see that chromium has to be 2 here because you have Cr2. Oxygen is 7, and you collect like terms and make Cr the subject of formula. You see that it is +6. And you have, let's consider examples of redox reactions. The first one here is combustion of magnesium to give us magnesium oxide. And you have it here that magnesium got oxidized because its oxidation number was 0. It got increased to +2 in magnesium oxide. That is oxidation. And magnesium is now the reducing agent. Oxygen is the oxidizing agent, so it got reduced from 0 to -2. In the second one, we have combustion of hydrogen sulfide. Also, sulfide ion got oxidized to sulfur, yellow sulfur here. We have that oxygen got reduced to oxide ion. So you can see the changes in oxidation numbers there. You have also the third example there. The third example of reaction between copper 2 oxide and ammonia. You can see the changes in oxidation number. Now here you can now tell which one is the oxidizing agent and which is the reducing agent. And you can notice that hydrogen ion and oxide ion were omitted. They are called spectator ions because they did not exhibit any change in oxidation number. Now we have that we can split these equations into half equations. Let's consider the first one, combustion of magnesium. You see the oxidation half showing change from magnesium to magnesium ion. It lost 2 electrons, okay? That is why we have the 2E there. You see the reduction half? Yes, the reduction half. Oxygen getting reduced. You now see the overall equation. That is very important. Okay, we now have balancing of redox equations. We can balance redox equations. In this case, our aim is to make sure that the number of electrons gained and the number of electrons lost are equal. Okay? You have this example here. We want to balance this redox equation. The first step to be taken here is to split into the oxidation half and the reduction half. Yes, you see that ion 2 got oxidized to ion 3 and chlorine got reduced to chloride ion. And the second step is to balance out the atoms and then the electrons. To balance out the atoms, ion is already balanced. You add 2 in front of chloride ions. You now multiply each side by the coefficient of the electron of the other side, okay? You use 2 to multiply that of ion 2 and ion 3 ions, and as well as their each electron. You have the electrons and the atoms balanced. Now you put the 2 halves together. When you put the 2 halves together, you eliminate, you cancel out the common terms. This is the balanced redox equation, or I call it ionic equation. Thank you. Now we discuss tests for redox agents. First, test for reducing agents. Number 1, to a solution of the substance, add a few drops of acidified potassium permanganate. The potassium permanganate gets decolorized. The second test is as follows. To the solution of the substance, add a few drops of brown ferric chloride, that is ion 3 chloride. The solution turns green due to the formation of ferrous ions, that is ion 2 ions. Now, test for oxidizing agents. Pass hydrogen sulfide gas through the solution of the substance on a filter paper. There will be a deposition of yellow sulfur. And the second test for oxidizing agents is as follows. Add a few drops of colorless acidified potassium iodide solution to the test solution. The solution would turn brown due to the evolution of iodine, which turns starch solution blue-black.
And don't forget to like and share this video, and also subscribe. We are committed to creating more videos for you. Thank you very much.